This is the third 3.2b video, and we're going to look first at how to write the equation of a regression line when they give us a computer output. So you can see here I've already got highlighted the important concepts, and this is from the Ford F-150 data. So we're using the miles driven to predict the price. So miles driven is the explanatory variable. So you can see the slope is going to be the coefficient of the miles driven. That's what this is here. The coefficient of the slope, or x, is 0.162. The y-intercept is going to be the coefficient of the constant. Technically, the constant of a line is 1. So it would be 1 times 38,257. A couple important things to realize. S is standard deviation of the residuals. R squared is 66.4%. I see students make the mistake of using the adjusted R squared value. You're not using the adjusted, you're using just the R squared value. We'll talk about these values later in the year. So write out the equation for this regression line. So you can see I calculated the correlation and the equation for the least squared regression line. The slope is the coefficient of x, and the coefficient of the constant is the y-intercept. To find the correlation, we're going to take r squared and take the square root of it. But I know that it's going to be negative and the slope is negative because the relationship between the price and the number of miles the truck has been driven is a negative relationship. So I know that from the previous graphs, there's that negative downward slope. So try and apply these concepts to do this independent practice problem. You can pause the video, but I'll keep going here. So another important thing about regression is that if we have the standard deviation of the x and the y values, and we have the means, then we can create the equation by hand. So if you look here, the slope of the regression line from y hat equals a plus bx, when b is the slope, all we need is the correlation times the standard deviation of the y values divided by the standard deviation of the x values. And we can find the y-intercept because every regression line passes through the point x bar, y bar. So if x bar, y bar is always a point on the least squares regression line, then if we have the standard deviation of the y values and the x values and the correlation, then we can always use the point on the line that we know to be true to solve for A. Let's take a look at an example to see how this plays out. So we have data from 15 high school students to investigate the relationship between their foot length and their height. The mean and standard deviation of the foot lengths are 24.76 centimeters and 2.71 centimeters. The mean and standard deviation of their heights, which is the response, is 171.43 and a standard deviation of 10.69 centimeters. The correlation between the foot lengths and heights is 0.697. Find the equation of the regression line for predicting height from foot length. So they've identified height as response and foot length as explanatory. Let's write out all of the information that they provided for us already. So since I have the means and the standard deviations and the correlation, all I have to use is my formula to find the slope and then plug that in to find my y-intercept. So here you can see I plugged in the standard deviation of y over x, solved for the slope. Then I plugged in x bar, y bar that they gave me as a point on the line to find the y-intercept. So solve for A, and you get 103.34. So the regression equation is the predicted height equals y-intercept plus the slope times foot length as the x variable. Next, I want to discuss something called regression to the mean. We're not going to dive too much into this, but it is helpful to understand what's going on here. So if you're looking at this chart, or this graph here, you can see that the regression line that we just found is right here in green. And then they've calculated they've started at the mean of the x values, which is right here in purple, and the mean of the y values is right here in blue. So you can see it passes through that point, x bar, y bar. If you go one standard deviation ahead in terms of x, it's going to take you to this green line here. And if you start at x bar, y bar and go up one standard deviation in y, it's going to take you to this red line here. That's what these mean, y bar plus one standard deviation. So what you'll notice is that when you go a full standard deviation above in terms of x, we don't go the full distance up. We only go up the distance of correlation. So the correlation for this value was, or for this equation was 0.067. 0.06, or not 0.0, it was 0.697. So for every one standard deviation in x, we go up or increase. The change in y is only the correlation. It's not a full standard deviation, it is 0.697 standard deviations. So we call this regression to the mean because the change in y is only changing by the correlation, and it's not changing as much as it does in terms of x. So you can see here, it's called regression to the mean because the values of y regress to their mean. So finally, let's look at how the slope, y-intercept, and standard deviation of residuals are influenced by outliers. We've already talked a little bit about this from 3.1, but just want to hit some highlights here and add in really one important thing. So here is a scatter plot showing Gesell adaptive scores versus the age at first word for 21 children. So they predict their score based on when they spoke first. So you can see there's a negative relationship, and they've shown the residual plot here, which appears to be relatively evenly scattered and no obvious pattern. And I want to look at 2 points, child 19 and child 18 specifically, because both of these points are outliers, but they're outliers for different reasons. Child 18 is much larger in terms of x, whereas child 19 falls right in the average x value, but it is higher in terms of y, so it's an outlier in terms of y. So one thing to make a note of is child 19, because it's an outlier in terms of y, has a large residual, but child 18 doesn't have that large of a residual because it's an outlier in terms of x. And so how do these points affect the regression? It's kind of obvious to see that 18 is going to be more influential, but the best way to determine if a point is influential is remove it and see how the regression equation and correlation changes. So here, this line is the original regression line with all 21 kids. If we remove child 18, this is where the line moves to. You can see a drastic change there. And you can look with all the children, we have a correlation of negative 0.64 and the slope is 1.127. If we remove child 18, the correlation is almost cut in half and the slope drastically changes. So that's showing that child 18 is an influential point. And let's look at see how it changes for child 19. Child 19, when we remove this point, now the line only changes this much here. So you can see that child 18 is much more influential, and you can also compare correlations again, negative 0.64, and it only increased to negative 0.76 or decreased to negative 0.76. So there's not as much of a change here. So even though both of these points are outliers, it's important to note that outliers in terms of x are the ones that are more influential on regression. And so that's what I've just summarized right here. Outliers in terms of x may not have large residuals, but they are more influential on the regression equation. And so the best way, like I said, is to delete the point and see how much the line of regression and correlation changes. So there are a couple of limits to regression. I want to make sure that I've showed you. It's important to make a note of what's explanatory and which is response. But if we switch these two variables, so if I switched it and got this new graph here, now price is explanatory and miles driven is response. The correlation stays exactly the same. But the regression equation, the slope, the y-intercept, that changes. So switching the two variables doesn't change the correlation, but it does change the regression equation. Also, I've said this multiple times, correlation doesn't tell the whole story. You need to look at the graph to really understand what's going on. Each of these points have the exact same regression equation and the exact same correlation, but you can see they're totally different graphs. So correlation is only used to describe linear relationships. Number 3, regression is not resistant to outliers. It's largely affected by outliers. And finally, just because two variables are associated or they have a strong correlation, it does not imply cause and effect. One example of that would be studies show that there's a strong association between a number of TVs that a person has and their life expectancy. So you'd think if you want to live longer, you should just buy more TVs. But it's obvious that there's something hidden there. People that have a higher income, or if they make more money, they have more access to healthcare, and they have more access to buying the things that they need to live a healthy life. And so their income is the hidden variable that's influencing how many TVs they have, as well as their life expectancy.